shall we start?
Yeah, anytime you want. Yeah.
Okay, good. So let me share my screen and we can start. Okay, can you see my screen?
Yes.
Good. So this lecture is not like a factual lecture. It's more a review of trends in NLP and deep learning in general as for winter 2018-2019. So we will take a look at the trends of that time and see where did that actually go. So if you have any comments, feel free to jump in and add your understanding. So first of all, as for winter 2019, he looks back 5 years ago and compares what they had at that moment to what they had 5 years before. And in 2014, we had no seek-to-seek models, no attention in NLP. And yeah, number of available data sets was much poorer, and there were no deep learning frameworks such as TensorFlow or PyTorch. And yeah, if you think of it, it's really a huge jump in NLP, which happened in that 5 years. And actually, after that, I think it was like the moment of 2019 is quite similar to what we have now. So we use the same techniques, but at larger scale. And let's see. Like predicting where natural language processing will go is quite difficult. And as you saw, probably no one could, in like 7 years ago, would predict it what would deep learning models be capable of in natural language processing. So in this lecture, he mentions the most prominent trends in natural language processing at that time. And the first one was using unsupervised data for machine translation and for NLP in general, and how using unsupervised data improves significantly the performance. The second trend was scaling up the models and where can you get it. And also he reviews some of the most controversial and interesting questions. And that's what NLP brings to us and what are the risks and what social impact can using much more efficient NLP models introduce. And also he reviews what are the directions of future research, and we will look how far did we went in the directions. So why was deep learning so successful? And before, in pre-deep learning era, there were a lot of sophisticated algorithms, and which required a lot of preprocessing and careful algorithm design to get some task. And like after deep learning really took off, what we could do almost always to improve the performance, like to throw more data and more compute into the task. And when we can do it, we will probably get better results. So here, comparison of performance for neural networks and other approaches to AI. And as you see, these other approaches had quite leveled up, and neural networks with a rise in compute and data availability really shine. And what are the most impactful applications of deep learning? So deep learning had great success in image recognition, and it's widely used in many real-world applications by Google, Facebook, and other companies. And so another application is machine translation, and also, as you know, like Google Translate uses deep learning in their pipeline to provide this really huge scale service. And also Facebook have done a lot of work in machine translation, and you can probably see like Facebook posts in many languages. And also there was like great success in applying deep learning to playing games. And you know, there was Atari games, AlphaGo, and now I think that in some constrained conditions, deep learning models have outplayed best human players in some how it's called, like MOBA games like Dota. Yeah, and so what was the reason for such a great success of deep learning? And one of the main reasons was a really huge amount of data which is available for the models to train. And yeah, we had this huge ImageNet data set, which is really one of the main reasons of the success of image recognition systems. And also we have a lot of language data available in the internet. And for machine translation, there are quite a lot of parallel data. And so this makes this application of deep learning possible. But if you look at the NLP datasets, we still have a serious like shortage of labeled examples and like labeled dataset. So how do we work with this? And the main approach is to heavily use unlabeled data. And we will look at some approaches to using unlabeled data for different natural language processing tasks. So at the first place, the parallel data for translation came from the domain where this parallel data existed naturally. So it was required, for example, for famous, one of the most widely used at the beginning dataset was English to French. And in Canada, there are two official languages. And so almost every official documents are available in both French and English. So that's why there is a lot of parallel data for these two languages. But for some other languages, there are not so much of parallel data, but there are a lot of data sets which are monolingual. And how we can leverage this monolingual data in translation tasks. So the most straightforward approach would be pre-train encoder and decoder separately as language models, and then jointly fine-tune them on parallel data. And application of pre-trained encoders and decoders really resulted in 2 points in blue score improvement. But there is a problem with this approach because there is no interaction between two languages at pre-training. So these two language models would be totally independent, and that would somewhat limit the application to translation. And what can we do about it? So we can train a language model to produce some translations on parallel data, and then use this language model to make more parallel data. And so that would be self-training. So this approach is somewhat strange because it looks like we're gonna train a model on the data it learned already. But we can slightly tweak this approach more and get more interesting results from it. And that would be, first, we use this language model to produce a translation, and that then we input this translated text to the model, which would translate in reverse direction. In this way, we have a good label, which came from the original text, but we can have somewhat noisy input to the translation model. And this actually yields a great result.
So the idea is you have an English to French translation and then a French to English back translation, but in your English to French translation, you can just initialize it with random numbers or whatever, and then you just train it so that when it goes through both models, it gets back the English that you put in?
Well, I don't think that initializing with random data would work. Basically, we first try to use some maybe small parallel corpus. Mm-hmm. So this initial translation should be at least somewhat reasonable. And later we can improve its performance, but by generating this extra examples for.
So do they use do they use cognates, like, because a lot of English words are similar to French words, and so maybe they use that as their first cut to try to translate based on cognates?
Well, there are like a couple approaches to get in this work, and yeah, we will look at that in a moment. But basically, I think this first approach described was actually like training on existing training these initial models in supervised manner, and then using this back translation extra data to improve the results. And this was introduced in this paper, Transformer plus back translation, which yielded plus almost 6 points in blue score, which, if you will look, this pre-transformer result was 26 points, and then transformer resulted in 2.5 or 2.4 improvement, and introducing this back translation resulted in great comparative improvement. And this was released in 2018, and I looked, and it is still state of the art as according to papers with code.
Wow. So this isn't really looking at solving the sort of the ab initio problem where you have nothing to go on. You already have a working language model, and then you improve it by using the back translation. Is that?
Yeah, that's right. And we will further look at this approach when you have no parallel data. So yeah, actually that is the next topic. And what if we have no parallel data? And so it would be a situation like aliens come to the Earth, and we need somehow to learn to communicate with them. Yeah, or maybe there are also some research in trying to understand dolphins. And I don't know what are the results there, but maybe applying some similar technique may help there, really. So the first topic he shows is unsupervised word translation. So this approach is based on the idea that relation amongst between words in different languages should be really similar. So for example, how crisis relates to money should be really similar with how this crisis relates to Geld. I don't think it's probably German, or I don't know what the language is. So, and yeah, it was like demonstrated in many cases that this relation between word embeddings are actually meaningful. And I think in the beginning of this course, we also take a look at relation between different roles, and that example like queen to king is as woman to man and stuff like that. So what we take from this, we have this assumption that structure of the word embeddings will be similar in different languages. And then what we try to do, we try to learn a projection which will match these two embedding spaces. And we impose orthogonality constraint on the matrix. So we learn a matrix W, which will project embedding in Italian to embeddings in English. And what this orthogonality constraint does, it so this matrix W, if it's supposed to be orthogonal, it can only do a rotation. So for this approach to work, we need to really to satisfy this assumption that both languages has similar structure. Yeah, and to train this, we train a discriminator which will try to distinguish between Italian word, the embeddings which come from Italian and embeddings which come from English. And the idea is that when this projection works great, the discriminator will not be able to distinguish English from Italian. So that's quite interesting approach, but we can like take a quick look to where did that go now, and that would be if you heard of XLM model, cross-lingual language models, what the approach they took. Can you see this picture from the figure from the paper?
Yes.
Yes.
Good. So what they did, they are training like shared vocabulary for many languages, and they concatenate English and French, for example, sentences. They add language embeddings to the positional embeddings and token embeddings. They add extra embedding for a language. And then they train this using denoising language modeling objective, but with this concatenated text. And in this paper, they demonstrate that this approach really results in really good, so here is this unsupervised cross-lingual word embeddings, and the cosine similarity and L2 distance between source words and translation is, so this model is performing better than previous state of the art. Okay, so that was like small jump into the future.
Question.
Yeah.
What is the token token in addition to the language?
Let me go back to that. Is it about this this scheme?
Yeah. So I get language embeddings are like the word vectors, right? Or is that not the case? I am trying to understand the difference between token embeddings and language embeddings.
So language embeddings it's an embedding learned for specifically this token, which corresponds to a language. That's like a marker.
Right, like that's like glove vectors or word-to-vec vectors, correct?
No, this is like this token embeddings are just like glove or word-to-vec embeddings.
Okay, so those are glove or word-to-vec. Then what is the language embedding then? It's just so, English or French?
Yeah.
Okay.
Like we add positional information, we also can add language information to this
So it's
token.
just
So
an
every
indicator
English
of the source language.
token will have added corresponding English vector.
Okay, got it. Thanks.
Okay, good. So the next approach we will take a look at is learning not a word-to-word unsupervised translation, but sentence-to-sentence unsupervised translation. And here, what they tried is really like smart approach. So first, what would this English to French translation look like? The model used here is simple seek-to-seek recurrent neural network with no attention module. So encoder outputs a single like encoding for the input sentence, and then decoder recovers translation for that. And also they input this language-specific token. The first token fed to the decoder would be language-specific. So, this model is trained with two objectives. And the first objective is when given, so we can consider this model as autoencoder. So it encodes the input sentence into a single vector, and then it learns to recover this input sentence from the compressed vector. And with no noise, it would be a trivial task to learn. And that's why model wouldn't learn any like too much language specific information. It will learn just copy the first token to the first position here and so on. And to make this more useful, they introduce some noise to the model. And there are two kind of noises they introduce. And first is dropping, for each token can be dropped with some probability. And the second kind of noise is with some probability, we can slightly shuffle this input sentence. So we don't want to shuffle it too much. We want to it to still preserve like semantic. But also we want this model to learn like really recovering this noisy input into original well-structured sentence.
So I have a question. So yeah, in my understanding, an autoencoder is always trying to recover the input text, but in this case, it's not trying to recover the input text. It's trying to recover a different reordered version of the input text. So how, in what sense is this an autoencoder? That's what I don't understand.
Yeah, it's a denoising autoencoder. So probably we start with copying input to an output, but then we introduce a noise. And in such way, we force model to learn something about language. So given a noisy input, it will try to recover a more probable naturally appearing output. And that's like one of popular applications of autoencoders. when like autoencoder, which is trying to generate reasonable text, will be able to recover noisy text into a more fluent version of it.
Okay, so you do start out with the correct version of the words, right? And then you scramble them and you try to recover the correct version again. Is that?
Yeah.
I mean, because if you start out with the scrambled version, you don't have anything to train with. So that's what I was a little confused by.
Yeah, actually, you still will have something to train, because you provide this fluent sentence as the output, so as the goal for this model. And it would be like similar to what the BERT, for example, training looks like. We also introduce some noise to the text, and what BERT trains to do is it trains to recover the original text from the noisy text, right?
Okay, right. So we do have the original, like you say, fluent version of the sentence. We start with that.
It's the target.
Yeah, and then we scramble it, and then we try to recover that target again.
Yeah, right.
Okay, thank you.
So, and the second objective is provided by this back translation approach. So what we do, we want to have, again, a fluent target, but we can make this input by generating back translations. And yeah, this is similar to what I described before, when you don't want your target to be noisy, but you can afford input to be noisy for the model. So actually, why does this work? And I don't know, I don't remember he mentioning this in the lecture, but actually there is like a third loss, which is they introduce a loss which makes sure that French and English outputs of encoder are not distinguishable. So this encoder will output an encoded version of the sentence, and we want English and French versions to be the same. So we also introduce some loss which will be provided by a discriminator, which tries to classify this encoding with according to from which language it comes from. So we have this shared cross-lingual embeddings, and actually what we end up with, this decoder should learn. So encoder should learn to output very similar vectors for the similar sentences in both English and French. And decoder should, it does not need to know from which language the input comes. It only learns to generate English text when you provide it encoded vector, and this token which corresponds to what language do we want to generate. So yeah, so this encoder output should be very similar for both I am a student and je suis étudiant in French. Je suis étudiant, okay. And these two models should be roughly equivalent. So no matter what we input, we should have the same output here. Yeah, actually, this model can be viewed as autoencoder, and that's why it learns to recover the desired sentence in desired language from encoded version of a sentence in the different language. Yeah, so this, as I said, encoder vectors should be the same for both English and French versions of the sentence. And if we compare the performance of this unsupervised models to performance of supervised models trained on different amount of data, as you can see here, it's plotted on log scale, and performance of supervised models is much better when we have a good amount of labeled data. But if the amount of labeled data is small, the unsupervised models outperform the supervised models. And another application he mentions of the similar approach is attribute transfer. So what is attribute transfer? When we have like two sentences with very similar meaning, but with different emotion, like attribute associated with it, we can train a model to like translate from relaxed sound to annoyed sound in a sentence. Yeah, that is another interesting application to this. And we will come back to this performance of unsupervised models later when we talk about GPT-3, because GPT-3 is actually now state of the art in some of unsupervised translation tasks. So, this approach has a very limited application to languages which are differently structured. So here he compares the performance of supervised models in English to Turkish translation and performance of the approaches described before. And word for word unsupervised translation, you can see it performs really poorly. And this another unsupervised machine translation also performs really poorly for English to Turkish. And that's caused by the fact that English and Turkish are very dissimilar in structure. So yeah, another approach to this is training this cross-lingual BERT model. And I already showed you this picture before with when we train a cross-lingual language model. Yeah. And still in like high resource languages, current state of the art outperforms by a good margin the unsupervised approaches. But for lower resource languages, this is English to Romanian, unsupervised models with pre-training are performing even better than state-of-the-art supervised models. And that's because amount of data available for English to Romanian is limited. So that's about application of the deep learning to cross-lingual translation. And before we move further to huge language models and GPT-2, and at this moment it should probably cause you to smile, because currently GPT-2 is not considered huge at all. So in that we had like huge difference between then and now. But yeah, I would like to switch to some extra slides I made, and about cross-lingual translation. Recently, Facebook released their multilingual machine translation model, and it works without translating to English. So it trains to translate directly between 100 languages, and it really performs great on all of these languages. So this is like current one of the most recent language translation models. So what did they do? In contrast to gathering like English to other language datasets, they gathered multilingual datasets where we will have all language pairs available. And then they train a shared encoder-decoder model, and they add extra specified layers, which would be split by language groups. And there are some criteria by which they select language groups, and those criteria are language availability and language similarity. So what we end up with is this shared encoder, as we seen before with that XLM model. And then we have a shared decoder, which is primed with which language we want to translate to, and also some specialized layers which work for a specific language group. That's how this approach works. And there is like interesting paper, and they released all the code for that. So for those interested in low resource translation, you should take a look at this pre-trained model by Facebook. So yeah, let's move further to the second trend, which he talks about, and that's like pushing the limit of the model size and looking at where can it bring us to. And yeah, he compares a number of parameters in different language models, and medium-sized LSTM model had 10 million parameters, and then we moved to 90 million of parameters with Elmo. And the first GPT had 110 million parameters, and then BERT, largest version of BERT, had 320 million parameters. And at that moment, GPT-2 was really huge with 1.5 billion parameters. But let's look at the number of parameters for contemporary models. And there was Megatron language model, and they train GPT-2-like model but with 8.3 billion parameters, and it was trained on 520 GPUs. This was a project by NVIDIA. And then Google introduced this T5, and like both of these models, and actually all of these models are not very novel in architecture. It's more like how can we push further the number of parameters and parallelize the training and to get more data and train really huge models, and what can we gain from this. So T5, the largest version is 11 billion parameters. Then Turing NLG by Microsoft have 17 billion parameters. And then we had GPT-3 with 175 billion parameters. And that's, you can see that's an order of magnitude larger. And later, Google introduced this G-Shard framework for training models, and they trained 600 billion parameters models. And the training was on 2048 TPUs. So, and they really measured the amount of computation needed for this model in like TPU years. And this growth of size in language models is related to technical optimization. And if you look at this G-Shard paper, it doesn't focus on language modeling. It mainly focuses on how can you train such a big model. So it's more like an engineering paper rather than natural language processing paper. And yeah, so Google introduced GPipe, and then Microsoft introduced Zero and Deep Speed for optimization of training very large models. And then Google introduced this G-Shard framework, which actually automates communication between a cluster of devices. So let's go back in time and again go to, so yeah, they compared a number of synapses in Honeybee brain to a number of parameters in GPT-2. And as you can see here, it's already surpassed by quite a great margin, but that's not like really fair comparison. The functions are pretty different here. Yeah, so he mentions that too, so we better don't compare apples with oranges and brains with language models. So, and this is general trend in all the directions. We have this growth, like logarithmic growth in the size of the models. And as you can see, this trend continues for now. Yeah. So there are huge models in computer vision. They were trained to achieve the best results. And he mentions this generative model for image synthesis, which was a large model by its time. And so he also shows this like linear relation, logarithmic linear relation with accuracy of models and number of parameters. So we have this like a log linear relation between number of parameters and size of the model. So yeah, and training of these large models is like highly related to these engineering innovations and architectures which enable to train these models. So what is GPT-2? It was like a really big transformer language model. So it didn't introduce that much of architecture innovations. So there were just slight variation to the original transformer. And it was trained on a very big data set for the time. And also they had an effort in designing this data set. So they don't want to use a garbage text data. They want somewhat high quality data. And how they did it, they used Reddit links, so text from Reddit with high karma. And now we can compare it to GPT-3. And GPT-3 is still just a really big language model. So not much novelty in architecture here. What they do, they just try to train a very big language model. And what is novel here is like very similar to GPT-2 is engineering part. And also how do we formulate these tasks for the model? How do we use this huge pre-trained model for few shot and zero shot inference, and we will take a look at that. So what did we have for GPT? So first of all, GPT was very good at language modeling, and these are results for language modeling for different data set. And this is zero-shot evaluation of GPT-2. So it was never trained on any of these data sets, and it introduced state-of-the-art on all of these data sets but one. And this 1 billion words data set is highly pre-processed, so it is not a natural language exactly. And it performs not so great only on this one data set, but it really outperformed all the state-of-the-art on other natural language generation benchmarks. And how can we use this zero-shot? What is the zero-shot learning? So to use zero-shot learning, we will try to leverage this good pre-trained language model and formulate the task for it to be like a language generation task. So for example, for reading comprehension, we input context and question, and then we have this answer double dot, and actually model encounters such kind of pattern in the text, and it learns after this a double dot to a column to generate an answer from the context to the given question. And the same for summarization. So we just put TLDR like token here, and usually in text after TLDR, we will have the summary of the article, and GPT-2 generates the summary of the article given this TLDR input. And the same is for translation and question answering. And let's look at the result of GPT-2. It was like what GPT-2 paper demonstrated, really, it did not match like state of the art on any task it was trained, but it showed this logarithmic trend in growth of the zero-shot performance compared to number of parameters. So what they demonstrated is that when we increase number of parameters, zero-shot performance of the language model linearly grows with the logarithm of the number of parameters. And so one question, how can GPT-2 be doing translation if it's just an English language model and it just encounters some multilingual text in its training data, and it learns to find the relations between, for example, French and English here. So it picks up from the training data just by looking at it. So GPT-2 demonstrated some reasonable performance in question, like open domain question answering. So basically we can just say it queries its it's like a querying model for an answer. So we input this question and we expect it to generate an answer for the question. And what can we take from it? It just really remembers that it is reasonable to generate Charles Darwin, who wrote a book, The Origin of Species, and so on. And in this lecture, he tried to extrapolate this trend and like how many parameters do we need to match human performance, for example, in reading comprehension. And it would be like 1 trillion parameters. And as you've seen, we are not that far from that mark right now, but we will look at the performance of GPT-3 and compare its performance to what we expected. But like this trend is not so clear. And for example, for summarization, it looks like increasing number of parameters didn't result in much better performance, for example. And another interesting thing about GPT-2 was a reaction to the decision of OpenAI not to release this model at the beginning. And we will also compare the decision of OpenAI in relation to GPT-2 with their decision with GPT-3. So, okay, let's take a look at GPT-3. And it was just recently presented in EuroIPS. I think this week there was a presentation. I don't think it is publicly available yet, but yeah, it's really like a current research. And first of all, they demonstrate here that even though GPT-3 has an order of magnitude more parameters than T5 and Roberta Large, like training, like computational cost for this model is lower, and they achieved it by applying this scaling law for neural language models from the other paper by OpenAI. So like a lot of engineering innovation in that paper. Also, they used much larger data set for that model. And here we can take a look at what data did they use to train GPT-3. And this is filtered common crawl data set. And they didn't actually use all the data from this data set, and it had like 60% of the training mix. And also they used web text, books, like 2 books data sets, and also Wikipedia data set. And you can see that the size of Wikipedia data set, which was considered like a great amount of data for pre-training a couple of years before, now it's just 3% of the resulting mix of training data for GPT-3. And actually it was seen multiple times when training by GPT-3. And what they demonstrate in this paper that this power law for accuracy, like model performance as compared to compute needed to train the model, we still can observe this linear trend. So if we increase the number of parameters, we can throw more compute into training, and model will achieve better results. And what is really interesting about GPT-3 is the formulation of the tasks for the model. How do they use GPT-3, which is, in general, it's just a very big language model. So autoregressive language model. What it learns is just to generate the next token given the previous tokens. But how can we use it to apply to different tasks? And there are like 3 formulations they used. And the first one is zero-shot inference. And for zero-shot, we just prime the model with task description and prompt. And model is never learned specifically to generate some specific output for this input. And the second approach is one-shot inference. And to do one-shot inference, we can not only give to model this task description and prompt, but we can also give it one single example of, in this case, translation. So what do we want? We tell model translate English to French, and we show it what would it be translate English to French. And here you see this sea otter and French translation for sea otter. And then we want it to translate cheese to French. So that's how the task is formulated. And we can do a few-shot learning. So we can provide it not a single example, but multiple examples. And their performance, they evaluated GPT-3 on many tasks. Actually, they evaluated it on superglue benchmark. And here, one particular result I wanted to demonstrate. And this is performance of GPT-3 on translation. So they, in paper, they consider 6 directions. And as you can see, model really performs great on translating from different languages to English. So how it works, it's just a really good English language model. And as you can see, it doesn't really need too many examples to learn to translate from English from different languages to English. And also, like, performance of in French is great because it encounters a lot of English and French pairs in its data. And you can see that English to German is somewhat worse. And if we compare it English to Romanian, which is much less frequently to be encountered in the training data, its performance is much worse. Yeah, and we can take a look at this paper briefly, and there are a lot of applications. They applied this model to different tasks, and like you can see here, they don't need really that much of examples to provide it for applying it to other natural language generation tasks. And they compare results of their model with different state-of-the-art at different tasks. And as you can see, it ends up outperforming state-of-the-art on trivia QA. This is a question answering data set. And it actually is question answering in so this is closed book question answering, which means GPT-3 is not given any context for the question. So it just generates this answer out of thin air. And it performs really great on particular data set, but it not performs as great for other data sets. And this might be related to how questions in the data set are formulated and how similar are these questions to what model encounters during training. Yeah. And also there are a lot of applications of GPT-3 to different tasks. And for example, there is this Vinogrande task. And in this task, really state of the art didn't match human yet. And but really it shows like a reasonable performance for this task. And also it here is interesting result. They compare question answering in so these data sets are requiring like some common sense reasoning. And this is like physical question answering data set. And they applied, it would be something like if I drop the ball, what happens? And like the ball falls to the ground. That's what model should produce for this data set, I suppose. And they get like really great results here, but not so great results on other similar tasks. And as you can see here is this note. And this note is that it might be that model seen this data during training. So it was exposed to example like this. And that's one point when you can wonder if the model learns to reason. So I want to say that, yeah, these tasks are supposed to require common sense reasoning, and they try to evaluate if the GPT-3 does something similar to common sense reasoning. and the result in this compromised data and novel data shows that there is really a gap in performance between the data it's seen and the data it haven't seen. And probably it means that reasoning is not what's going on inside GPT-3 exactly.
Artes, what is the state of the art for that? Which system is the state of the art for common sense reasoning?
I haven't looked at what is the state of the art for that particular task.
Okay.
So. So, and also there are, or I accidentally closed those slides. Let me reopen it. So, there is an effort to demonstrate that few-shot learning is not only applicable to very large models, it also is applicable to smaller models. And there is this PAT training framework, which is like pattern exploiting training. It's short for pattern exploiting training. And there is a paper which demonstrated that with formulating a training objective in specific way, you can achieve even better than GPT-3 few-shot performance using Albert as a backbone for the model. So there is one interesting area of research that actually you can really achieve good few-shot performance on small models. Yeah, so, and like another thing to compare between then and now. So when GPT-3 was released, their argumentation for not, they had this like multi-stage release of the model. They first released smaller models and then larger ones. And they gave like access to the model through API to researchers to be able to evaluate the model. And after the GPT-2 model was released, there was a lot of discussion on this release policy OpenAI adopted. And many researchers were furious that for the fact that they did not release their model straight away. And now we can go forward to GPT-3, and GPT-3 is now available through API, and that's a commercial application. There are also, like, they gave access to the researchers again through API, but also they have this commercial API, and also it is licensed to Microsoft. So yeah, Microsoft is one of those biggest corporations which can leverage this natural language models, and yeah, as you can see, like the approach is very different. And also another thing which is different compared to GPT-2. So GPT-3 provoked a lot of discussion about limits of the huge language models in terms of common sense reasoning and general artificial intelligence, and how close is what GPT-3 doing to what we expect really general artificial intelligence to do. But probably you are exposed to some of this on Twitter or in news, and yeah, so it actually changed somewhat. And to continue with this scaling of the models, we can move on to this 600 billion parameters model trained by Google. And I will not go into details of that model. It is like their approach to scaling of the model is quite different to GPT-3. So GPT-3 was a really deep model. So the number of layers is much higher than usual number of layers in language models trained before. But in this experiment, Google used a different strategy. And as you can see here, their largest model is only 36 layers deep, but they use this mixture of experts approach. And what is mixture of experts? We have like this sparsely gated rows of data, and there are like attention module is parallelized in regular standard way, like it's data parallelized across devices. But feed forward part of the model is it is like we have separate feed forward module for each device, and it is each separate feed forward module is specialized. And this is result. They use this training approach to train a translation language model for translation. And this graph shows increase in blue score. So you see this is not a blue score. It's change in blue score compared to their baseline. And as compared to number of available examples. And this part is like high resource languages. And here we have low resource languages. And there are different approaches to training these models compared. And low resource languages, the best result for low resource languages we have for not for their largest model, but for this 150 billion parameters model. And what is happening here, that some experts which are specialized on low resource languages, they are shared with other languages, and they learn to utilize some shared knowledge of language between different languages. And in such way, we can benefit in low resource language domains. And this model is not released yet. And so even if it was released, I don't know who a part of the largest corporations can like really take a use in of 600 billion models. So yeah, this brings us to another topic of how these great models might be used. So yeah, here are the results of training from this G# paper, and as the models gets bigger, they have a bigger improvement in blue score, and they demonstrate that this new approach to scaling models. So here is the deepest model is 36 layers deep, and before they used this G-pipe to train 96 layers deep model, and its improvement as compared to computational cost was not such a great improvement. Yeah. So, and he discusses the GPT-2 reaction, and I don't know if it's really relevant now, because at that time it was really like a hot topic on social media and in natural language processing community, but by now like focus have shifted from that, I think. And like there are a lot of opinions on if their GPT-2 should be released, and the opinions were different. And I don't know if you want to share any opinions on that, we can go on with that. If no, we can move further to the next topics.
Sure, you can move on.
Yeah. So there are arguments for releasing these models and for not releasing that models. And like in general, you can say that not releasing GPT-2 was like of the having this large language models like GPT-2 was inevitable at that point. And but now the models are much larger, and it is really not feasible for anyone except the largest AI corporations to train models of 175 billion parameters and so on. And yeah, it really takes a lot of time. And another point about GPT-3 is that it is trained before the coronavirus, and it so happens that it has no information about coronavirus in it whatsoever, and it makes it somewhat less relevant, even though it is really like current research, and it cannot be easily retrained to incorporate new information. So still this upscaling the model size is somewhat limited in, so it has its limitations still. Yeah, and another topic he mentions that actually discussing this discussion of this GPT-2 release was going on mainly inside the machine learning community. But actually the results of AI application in general has broader impact on the society. And so it's probably like a good time to consider different options for control over how artificial intelligence is applied in a real world. And here he mentioned some examples of like flawed application of AI, and there are different there are a lot of examples, and we have discussed some of them at the previous lecture, which was dedicated to bias in AI. And the next thing we can mention is different applications of AI and with their new potential. Like we can apply AI for to make great chatbots, but there are also a great risk of doing so because we still don't understand what's going on inside these models, and that's another topic to discuss. Okay, so another interesting thing, at that moment, he was comparing the state-of-the-art model for that time with human performance on glue benchmark. And we can compare current state-of-the-art with glue on glue benchmark, and here is the last line is human baseline, you see, and really the new models outperform humans on glue benchmark. And it was initially supposed to be like a method to measure ability to generalize for language models. And now it isn't relevant. But at the same time, we didn't solve natural language processing yet. And so what we come to is we need some more difficult benchmarks for these new models to train. And therefore, superglue was introduced, and it was considered like very difficult. And as you can see, human score for superglue was around 90. And their baseline was fine-tuned BERT model and improved. And it was there was almost 20 points margin at the time when superglue was introduced. But by now that gap is closed, and you see T5 is the best performing model in superglue. And it is really very close to human performance, and it outperforms humans on some tasks, but on some other tasks, it is performed less good than humans. But if you take a look at the numbers, almost all of those are pretty close. So there are no one particular task which model cannot perform at all, like, or performs real bad on it. So, and what did this introduction of transformers and BERT did to natural language processing? And he asked the question whether it is death of architecture engineering or what is going on with this area. And we, as you remember, we 2 lectures before, we considered that super complicated model for multitask learning. And what is T5? T5 is another multitask learning model, and it is its architecture is really very similar to standard transformer. Nothing special about it. And yeah, attention is all you need. Simply replaced all the fancy architectures. But actually, there are some other tasks in which naive application of language model is not so good. But he also mentions that top 20 entries on Squad dataset leaderboard are using BERT. And these are different variations of BERT applied to Squad. And so there are some tasks are pretty close to or even better to human performance, but there are other tasks in which natural language processing models are not doing as well. And these tasks are those which require something closer to common sense reasoning, I guess. And there is research in designing more challenging data sets for these models. And one example of it is this Squawk question answering data set. And it requires a model to answer the question given some context. And for example, it would be like extraction of the answers from Wikipedia article. And really it's, I have a look at leaderboard for this data set, and human performance is not matched there yet, but it also doesn't seem to be very popular inside NLP community right now. So maybe it is not closed because researchers are not trying to close it that hard as with, for example, that superglue task. But still, there is some considerable improvement on the state of the art since 2019. And this is another data set in which human performance is not achieved yet, but really the scores model are receiving on this task are now around 84. And as you see, it was around 60 average score here would be, yeah. So really, there is some progress, but not yet. So he notes that at that time, best performing models on Glue benchmark was multitask trained models. And actually, it happened so that still best performing on SuperGlue benchmark is multitask trained T5 model. And he mentioned some other limitations of language models for now. So we have great performance in high resource languages, but what's going on in low resource languages, and the performance there is getting good performance there is still challenging. And one way to bridge that gap is using this cross-lingual models and training models on cross-lingual data. And now, for example, due to Hugging Face, there is available a lot of publicly and easily accessible cross-lingual models. And there is another event, which is dataset event. They are gathering new dataset and encourage people to publish datasets in low resource languages. Yeah, so we have some progress here as well. And another area which is quite interesting is interpreting and understanding model predictions. So to apply natural language processing in real world, we might want to understand why does it do certain prediction added additionally to what it predicts. And yeah, I have here a couple of links to research in this direction. So one interesting paper is called Right for Wrong Reasons. And they actually discovered that for a particular task, a model learns to apply 3 fallible heuristics, and while it performs really good for some data set which it was fine-tuned for, it is really easy to construct adversarial data examples in which causes the model to fail because it applies this special heuristics to perform the task rather than really understanding the underlying problem. And yeah, I encourage you to take a look at this paper. It's one interesting one. And another paper, and this one is one of co-authors is the professor which leaded this course, and there they have explored what actually BERT attentions matrices are looking like. And yeah, that's another interesting paper which we don't have time right now to go into details, but here is a link, and they have like a lot of nice examples there, and you can also take a look at that. And another like a very recent paper in which they claim that a knowledge graph can be parsed from a language model, and they used pre-trained language models to parse the knowledge graphs. And in this paper, they did not do any fine-tuning of the model. They took, I think, BERT and GPT-2, maybe GPT-3, and used those to, and applied some rules to extract knowledge graph relations from their language models. And the results presented in that paper are both interesting and somewhat controversial. And yeah, that's another interesting paper to take a look to, and it might have some insight of what model learns. And just I'll quickly mention another research direction in natural language processing, which was not mentioned in the lecture, and that is direction of efficient transformers. So the attention is a memory bottleneck of the transformer architecture, because attention matrix is quadratic in size with respect to sequence length. So in this way, transformers are limited to some shorter sequences. And there is a lot of research in a direction of feeding much longer sequences to transformer-like architectures. And yeah, that's a really interesting area of research. And actually there are like a lot of different approaches to applying sparse attention. And here is another recently released paper, which is called Long Range Arena, where it is by Google, and they designed a framework for comparing results of this efficient transformers architecture. So they evaluate the performance on different tasks, specifically designed to measure ability of a model to train on longer sequences. And yeah, they're going to release their code, but it's not released yet. So that's another interesting paper. And this is just an example of sparse attention map. And this one is specific to this big bird model. And as you can see, they combine different sparse attention approaches to receive their attention model. So you can see like we can attend to the only to neighboring keys, and we can attend to some random keys, and we can attend to all the keys for some queries, and for only for some keys for other queries. And in this big bird model, they combined all these approaches, and it is currently the best performing model in this long range arena benchmark, but it also not very computationally efficient. Okay, so let's get back to this lecture. Yeah, so yeah, he also mentions this application of diagnosing or probing classifiers to BERT model, and these are the graphs of this classifiers applied. They applied like took output of different layers from the BERT model and compared the performance on different tasks. And here you can see that they get the maximal performance for part of speech tagging, taking the embeddings from 6th layer, and which may be interpreted as like this middle of the BERT is responsible for some information which is similar to this part of speech information. But for sentiment, the best performance is observed for the latest layers of the model. And there is this dependency parsing task, which is somewhere in between. So, so in this way, we can understand somewhat what information is learned by BERT on different depths. Yeah, and he mentions some of the most interesting applications, like hot applications at that time of deep learning and NLP in industry. And one is chatbots. So all their IT giants like Amazon, Google, Apple, they have their smart assistants. And you know, there is Alexa, and there is Alexa Prize, which is established to like enforce research in the domain of dialogue bots. And really, we recently in our paper reading group had a look at one of successful entries in this Alexa Prize challenge, and they had done a lot of handcrafting of the features, and it is not really this simple end-to-end encoder decoder architecture. It is a lot of handcrafting and a lot of like using templates and stuff. So in industry, when the performance and reliability and response time are relevant, we still are not 100% in deep learning area. There are still a lot of handcrafting going on, and probably a lot of like opportunities to improve. And another area of really like hot area of research is healthcare, and the number of medical papers published is much larger than the number of deep learning and machine learning papers, and really some strong NLP models for understanding medical text would might benefit a lot in the area to highlight relevant research for those interested. So the takeaway from this lecture is we had a rapid progress in last 5 years, and it continues till now. And yeah, there is even more rapid progress, and still NLP is a hot topic. And the NLP research has a big social impact, and it is it is a good idea to consider it more broadly. And yeah, that's it for the lecture.
Thanks so much, Arto. We don't have much time because the Kaggle meeting's coming up in a few minutes, so we don't have really time to discuss this, but let's continue on the Slack group to discuss what we want to do as a follow-on. Perhaps we want to start a paper reading group or something. Let's keep that discussion going. So I want to thank Arto for taking on that last lecture. That was really great. And yeah, good luck to everybody. Have a great